engineering, technology, and strategy at Embraer. This is a very special briefing in the sense that we are bringing together the manufacturing community to talk about the issue of cabin air quality, which has been, during this COVID crisis, a focus of significant concern. And what we'd like to do today is to present you with some research that the manufacturers have been doing, as well as an overview of in-flight transmission from our Dr. David Powell. So without any further ado, I'd ask David to take the floor and take us through the first part of the presentation.
Okay, thanks, and very sorry for the glitch which just happened as we went live. I can't see your version of the slides, but I have my own in front of me, so I think we'll be just fine. And of course, this is a year when normally by now, many times as many people would have flown as have done so, and most of us haven't been able to do so, mostly because either the event we were going to was cancelled or we weren't able to enter the country we planned to go to. But one of the things that we've been anxious to do all year is ensure that the actual environment of the travel journey is safe from end to end when that journey becomes possible again. And so we've worked closely with our airport colleagues and other partners, particularly through the umbrella of the ICAO CART, Council Aviation Recovery Task Force, to create what's been called the public health corridor. And that's just really looking at the end-to-end journey. So that's on the next slide, which looks at various ways from start to finish that the journey can achieve distancing and avoidance of sharing contact with the same surfaces, thorough cleaning and sterilization of sanitizing of those surfaces. And of course, something that we've advocated since June, which is face coverings for all travelers. Alterations to the actual service on board to minimize that direct face-to-face contact with other people. And of course, similar measures at the other end of the journey. And these have been well publicized. But I think today we're focusing more on the actual journey on the aircraft itself. But before we do, the next slide just indicates what people are saying to us in customer surveys about what they perceive. And interestingly, of those people who have traveled, the great majority say that they felt that their safety was being taken care of well during the journey. Interestingly, for us, there is a kind of a mixed message there about cabin air quality, with people perceiving, on the one hand, that they understand the air is as clean as a hospital, and on the other hand, that they have concerns about cabin air and that their main concern is from those sitting nearby them. And I think those messages kind of reflect the reality that the air that's supplied to the aircraft is very clean, but that's the risk that remains is from those who are nearby who could potentially be carrying the virus and perhaps unaware of that. So we'll come back to those points. But first, what we wanted to do is turn to what's been published about actual transmission of COVID during flight. And I want to call this flight associated, because in any of these cases, it's usually not clear when the transmission occurred. It could have been before the flight, during the boarding or disembarkation, or in the airport journey. So we'll have a brief talk about these, but let me just point out that this is an almost complete list of what's been published in peer-reviewed literature. I did leave out a couple of studies which were preprints, so not peer-reviewed, and they really provided no information about why the authors had asserted that it was in-flight transmission. So we really couldn't evaluate them. There are also a couple of studies left out which showed no suspected transmission, and I just left them out because the slide was not leaving enough room. But what you see on this chart is that for the most part, those instances where the authors thought there may have been flight-associated transmission, mostly it's one or two people on any given occasion. And there are two obvious exceptions on the page, which I'll come to, but mostly it's one or two, and the vast majority of these also are from early in the year. Two things about that. So firstly, obviously that's when travel was much greater, but the other thing is that at that stage, mask wearing was uncommon. And so things have changed as the years gone on. The travel has reduced, but also mask wear has become much more common, and we haven't really seen transmission other than in very tiny numbers. You'll see there two instances where it's suspected that in the course of the flight there was transmission to multiple other people. The first one, London Hanoi, up to 15, so 12 other business class passengers, 2 in economy and 1 cabin crew member. Unfortunately, this study doesn't have the genome sequencing, which makes the determination much more definitive. However, in terms of clustering in time and space, it does look like that's a flight-associated event. And indeed a sort of super spreader event. That was somebody who was unwell at the time and unmasked. The other one, Sydney-Perth, involves 3 primary cases and up to 11 secondaries, and this one is supported by genome sequencing. And so that one is of great interest to us. Again, back in March, again, when mask wear was uncommon, and the primaries were passengers exiting from a cruise ship. And finally, on this slide, you'll see there a reference to IATA Medical. This is from the contact that we have with a large number of the world's airlines through their medical contact people. And we obviously solicited any suspected cases that they were aware of flight-associated transmission. We initially got none, but we probed more closely with a number of airlines who had close contact with their public health authorities. And the initial analysis there is a small number, 3. It may be a little more than that, and some analysis is ongoing in detail. One particular country had 700 known primaries, so that's people who flew while infectious with COVID, and from those 700 had just 3 or possibly 4 known or suspected secondary cases. And the last line in the chart there refers to CDC. It was published, you would have seen in Washington Post recently that they'd followed up 1,600 primaries and had no secondaries, but communications to us from CDC say that the number is not 0, however it's very low, and we expect to see it published in literature soon. So there we are, that's the summary, and if we go to the next slide, totaling up those it's around 44. Maybe it's a few more or less, but that's a tiny number, because even this year, at this point, 1.2 billion people have travelled. So we're talking about one secondary case from the flight for 27 million travellers. Now, of course, this may be a gross underestimate of the actual number, but you can see that even if the real number is 10 times that, we're still talking about very, very low numbers. One of the comms teams sent me figures from CDC for lightning strike. It's two different figures published in the US, but they're 1 in 500,000 people per year, averaged over a number of years. The other figure was 1 in 1.2 million people per year for lightning strikes. So they're very different events, but it's just giving us an idea that this is an uncommon event. And so does that make sense for it to be so rare? Is that plausible, and why might it be so? Well, that's why we've brought the aircraft manufacturers to the table to discuss this, and just to sort of give a prelude to some of what they'll discuss. We know that a number of features of the airline cabin have effectively designed in protections against transmission of airborne organisms, and here are a few of them. Simply that people sit still, they face the same direction rather than face to face with each other. They don't tend to sing or speak loudly. And of course, they don't tend to fly when unwell, so coughing and sneezing is not as common as in some other situations. The seat backs themselves act as a physical barrier. And you're going to hear more about the airflow, but it is designed to minimize fore and aft flow of air, and the flow rates are high, and any recirculated air goes through high quality HEPA filters, and that's where the comparison often comes into hospital air supplies. So I'm stealing the thunder of our esteemed guests from Airbus, Boeing, and Embraer, and we'll stop doing so and hand over to them. Thank you very much.
Yes, Tony, you're muted. So thank you very much, David. Thank you very much, David, for setting the scene. I think it's quite clear and very clear what you said. And by the way, you could be doing an excellent job on showing the air system into an aircraft, because I have not much to add after that on the basic features of it. Let me share with you some more advanced and detailed work we have done in the recent past. So as David said, since the beginning of the pandemic, we have consistently repeated that the air in the cabin today, by design, is protective. I would say is safe. The air is fully renewed, as you said, every 2 to 3 minutes. So that's a very high pace renewal. There is a constant injection of fresh air as you cruise at 35,000 feet, minus 54 degrees Celsius. Of course, nothing is living there. So no virus can be ingested, I would say, in the aircraft while you're sucking in the air. Any air which is recirculated goes through HEPA filters, which are filtering 99.9% of all particles. There again, the virus is filtered as well by these filters. And the pattern, the flow pattern, which is on board the aircraft, is somehow washing everything that is in front of you as passengers, and very rapidly in a few seconds, I would say, removing anything from the cabin downwards under your feet as the air is exiting from the aircraft, and then exiting the aircraft completely out of it. The back of the seats, of course, is also a protective barrier. And all this, by the way, is not by chance. It's simply since the creation of ICAO in 1944, at its origin, the Article 14 reminds that the signatory states are there also to protect the passengers from being infected on board an aircraft. So really this safety of flight in all its sense, including the health, is into the DNA of our industry since decades at least. Next page, please. However, we also recognize in June, I would say, that we're still seeing fears into some passengers, and we wanted to do some extra work and to make extra check of how droplets, as emitted by a cougher or a talker in the aircraft, would circulate and therefore could potentially contaminate somebody by transporting the virus. To do that study, we started by using our very detailed 3D computational fluid dynamic model that we used to design the cabin flow for years. This very good, very strong model has been also tested and identified in front of real data coming from flight tests or ground tests. So really, we know that the theory and the mathematics behind the model is really matching the reality of the ground of the flight. We asked also medical specialists to tell us what they think is important whenever we want to inject a human event, once again, breathing, talking, coughing, into this model. And they were of a great help for us to understand what we had to modelize. The model is in fact meshing more than 15 million data points inside the cabin. And for each of these 15 million data points, we're computing the airspeed, the direction, the temperature, and the number of droplets, of course, passing by. And we repeat this calculation up to 1,000 times to represent 1 second in real time. So the analogy I make is with the TV set. When you watch a movie on your TV, whenever you see 1 second a movie, you have in fact seen 60 still frames at the frame rate of 60 per second. And here we're talking about basically 1,000 frames per second that we calculate. Once again, to give you an order of magnitude, to represent 4 minutes of actual life, I would say, into the aircraft, it takes us 10 hours to calculate on computers, and we do have good computers to do this calculation. So it's really a very intensive calculation, so a very representative model that we use. So we took this model and we seated the passengers in every single seat, and we equipped as well the simulated passengers with a mask, because that's the standard by which we abide. Modelizing the mask was also a good effort on our side, because it's both a device which is protecting and filtering, but it also has some leakages, and we wanted to show these leakages and to take into account these leakages into our calculation. And we made hundreds of simulations to test all the potential cases, everybody with masks, some passengers not wearing the mask correctly, different airspeeds, because the pilot can tune the airspeed on the aircraft as well. Humidity, temperature can change. The location of the person who is coughing is also can be changed as well. And really wanted to explore all the space, I would say, that can be explored with that kind of simulation. Next slide, please. At the end of the day, that's what we found. So keep in mind, one cougher, seen somewhere, is going to expel, in our model, is going to expel 10,000 droplets from various sizes, by the way. It's a distribution of sizes from very, very small droplets, 1 micron, to large droplets, 750 microns. So the cougher is going to expel 10,000 droplets. He's wearing a mask, he or she is wearing a mask. So the mask is going to stop some of the droplets, the biggest one, by the way, generally, okay? Then the gravity is going also to, I would say, catch the remaining droplets which go through the mask, and the droplets will fall on the ground in front of you. The smaller droplets will continue to float into the air, but the airflow of the aircraft, as I explained, is going to wash that very rapidly as well. Some particles, some droplets will still go through, and they will be stopped by the mask of the person who is receiving, who is breathing. And then at the end, out of these 10,000 droplets, only 5 at maximum will reach and will be inhaled by the person who is breathing. And this person can be seated next to the one who is coughing. As I said, as I remind everybody, we have fully loaded aircraft with all seats occupied by passengers. When we looked at this figure, 5 droplets out of 10,000, from I would say the common sense, you can already see that probably it's not very, very infectious, or that the probability, I would say, to be infected is quite low. We shared that with the medical specialist as well, and clearly they were not worried by the figures that we were showing them with these 5 droplets. However, they also learn, I would say, and discover the disease and the infection as we go. And they are not today in a position to guarantee that these 5 droplets cannot be infectious for somebody, or at this stage they could not do it. So we decided to, in fact, go further and compare it to a medical yardstick. And the medical yardstick that we use today is the social distance, the so-called physical distance, depending on the state. Some countries are speaking about 1 meter, others are talking about 1.5 meter. We took the most conservative one, which is 1.8 meter or 6 feet, coming from the US CDC. And we did exactly the same thing as with the aircraft. We simulated with our model one person seated in an indoor environment, coughing, and we seated persons 6 feet apart from this coughing person. And we also looked at the number of droplets that the others, being 6 feet apart, would inhale. And when we did that with the same model, what we found is that people could inhale 10 particulates, 10 droplets at maximum. So think about it. When you're on the ground and standing 6 feet from each other, you could eventually inhale 10 droplets. When you are sitting in an aircraft next to each other, wearing masks, with the airflow, washing constantly, at maximum, you could inhale 5 droplets. So that means clearly that the aircraft is even safer than the recommendation that we have from authorities today to be standing or sitting 6 feet one from each other on the ground. So as a conclusion, and here even with this medical yardstick, we really can say that the risk of being infected through the propagation of droplet in aircraft is very low. Thank you. Back to you, Tony.
Great. Thanks very much, Bruno. So I see we've got a few questions started in the queue. We'll go through each of the 3 presentations before we start to take questions. So what I'll do is I'll ask Dan to join us now from Boeing and take us through his presentation.
Great. Thanks very much, Tony. So the Boeing research has been done independently of Airbus and Embraer, but also very much in a similar way. We've done a vast amount of particle movement studies inside the aircraft and in other environments to understand the relative risk of air travel with regard to aerosol transmission compared to other normal activities that people will engage in either at their departure or their destinations. It's also important to note that aerosol transmission is one method of transmission. We're not focused on it here, but there is a cleaning program and surface or fomite transmission that the airlines are very focused on and working with the airframe manufacturers to ensure that the right technologies and chemicals are used for protecting passengers from that. But we're focused on the aerosol transmission here. And similar to Airbus, Boeing has done computational fluid dynamic analysis to track particle movement in the cabin. We use different software. We have different architectures in the airplane, but we've got a similar approach, and we've confirmed our assumptions to ensure that we're consistent and conservative in our analysis. We've analyzed single-aisle airplanes and twin-aisle airplanes. We've also done many scenarios with people breathing, people coughing on full flights with masks and without masks. We'll have people coughing from different seats in the airplane and making sure that we account for the gasper or the airflow nozzles above the passengers being on or being off, all in an attempt to understand what's the worst case scenario when we have a cougher and a breather on the airplane that, where we can have a transmission of a virus. We have also been working to validate that computational analysis with live testing. So we have done testing both on the ground on airplanes on the 37, 67, and 777, as well as in flight, where we do a simulated cough with particles and then have sensors on the airplane to measure the volume and the location of where those particles go. And those that live testing has been really valuable in making sure that the analysis that we're doing is reflective of real life, the real physics, both on the ground and in the air. If you go to the next page, please. So we're trying to relate the airplane risk of transmission compared to other common scenarios. And so we've picked two other scenarios to do the comparison. The first one is what we consider the worst case for an aerosol transmission. It's where we have a cougher and a breather that are both in an indoor environment with stagnant air. There's no airflow. And that means that there's no airflow to disperse the particles. The particles come from the cougher, who's pointed at the breather. They expand in a conical shape. And we measure the number of particles in the breathing area of the breathing person at different distances. So as Bruno mentioned, the heavier particles will drop out of the path because they're heavy and due to gravity. And the cough, because it's a conical dispersion, not all of the particles from the cougher will get to the breather, and we've done simulations and understand how many particles will come in the breathing area. The next scenario is a conference room where we'll have standard building airflow, air coming in and air exiting the building. And we have a cougher in the room, maybe at different locations, and then we measure the particles in the breathing space of people in different distances away from where the original cougher was. And then finally, we've done extensive work on the airplane and understand how particles move in the airplane with, as I mentioned earlier, with coughers in different locations. And all of these simulations have the airplane is completely full, including middle seats being occupied, to make sure that we're really addressing the worst case for both the cougher and the breather locations. And again, the message, the thing that we're measuring is the number of particles in the breathing space. As Bruno mentioned, there's medical doctors don't understand now how many particles it takes to become infected. And we're certainly not in a position to know that either. And so rather than saying what the likelihood of infection is, we're using the number of particles in the breathing space as our method of comparison, which we think is a good, solid method of comparison. So the results of our analysis is that if you look at the airplane, full flight, cougher sitting next to the breather in the worst case with the worst airflow, et cetera, what we found is that that compares the number of particles in the breathing space compares to being greater than 7 feet away if a cougher is in an indoor environment in a stagnant airspace, and also greater than 7 feet away in a building environment where there is some airflow. And we're using the greater than. We're not providing the exact number of feet at this point because we want to be conservative in our analysis. It's really important that we don't overstate that, but we are very confident that the number of particles in the breathing space in both of these scenarios is greater than 7 feet when compared to the passengers and coughers and breathers on an airplane. And so that really is an independent way of reinforcing what Bruno mentioned with the Airbus analysis. Again, different tools, different assumptions, different airframe, different airflow, but very much the same conclusion, which has also been validated by our on-airplane testing. If you go to the last page, it's simply a summary that shows an airplane view or a layout view with all of the places on the airplane with an effective social distance between the coffer and the breather of 7 feet based on particles in the breathing space. And with that, Tony, I'm going to go ahead and turn it back to you to continue the presentation. Thank you.
Great, thanks very much, Dan. And so I see there's some more questions coming in. That's great. We'll get to those, but we have one more presentation from our friends at Embraer. So I'll turn it over to Luis Carlos to take us through the next section.
Thank you, Tony. Good afternoon, everyone. It's a big pleasure for us to participate of this IATA media briefing. So let's go to the next slide, please. So as we compare the cabin of an airplane to the cleanest of the environments in our lives, we see that a hospital operating room has 5 exchanges per hour in terms of the outside air and the air volume inside this operating room. Whereas, next slide, please, we see that in an airplane, we have 20 times outside air changes per hour. So basically, every 2-3 minutes, we inject inside the cabin of an airplane a volume of air equivalent to all the air inside that cabin. Next one. As my colleagues have shown, this is a pretty standard architecture in an airplane. The air coming from the top to the bottom, washing, all the particles away from the head of the passengers, helping gravity to take all particles and viruses and what have you through the grills outside the airplane. And as well as preventing a cross cabin or a cross rows mix of the air inside the airplane. Next one. And, the general public is always surprised by how efficient the HEPA filters are. But yes, they can filter with a huge efficiency particles the size of the COVID virus, like 99.9+% of particles the size of a COVID virus. All the airplanes that are in our production lines are equipped with HEPA filters. Next one. And the HEPA filters are required to be maintained regularly. Our industry is a very regulated industry. So the HEPA filters are maintained. We did not have to change any maintenance interval after the pandemic. So whatever we were doing for years in terms of intervals are good enough to keep that efficiency level in filtration. Next one. And like our colleagues, slightly differently, but we also, since many years, we have been using computational fluid dynamics studies to simulate the airflow inside the cabin for several reasons, including air quality, but also for noise, for comfort, and so forth. So in our case, we have a mesh of 60 million dots, and really we use like thousands of CPU cores to to run it. So it's a very sophisticated model that we have for the entire cabin. Next one. And we have validated, tuned these models in a full-scale mock-up, as you can see in this picture. So with that, we perfect the model to have a higher fidelity. Next one. And we complement that through lab tests that we have been doing with several partners, the academia, ICAO, NASA, SAE, Fraunhofer, IATA, and several of other players in the industry. On the left, you can see particles being measured through laser. On the right, you see air quality tests with a mannequin there, coughing and air quality being measured in other locations. With that, we can say we have a very, very high fidelity model for air movements and particle movements inside our cabins. And this is what we have used to analyze the scenario under the COVID-19 scenario. Next one. And so this is what we did. So we basically simulated a 7-row droplet dispersions. Our analysis slightly different from that of Boeing and Airbus. We did consider a certain mass, 200 micrograms in a cough, distributed in 16 droplets diameters. It was an aerosol analysis too, but more based on the mass inside a cough. And these different sizes ranging from 0.1 micron to 200 micron. And in several scenarios, gaspers on, gaspers off, masks on, masks off, different positions inside the airplane. So we computed all this. And in the next slide, we see the results. In which, so if you look at the right, we see with passengers wearing masks, only 0.02% of the coughing mass will reach the breathing zone of the other passengers. We can also see that if you don't wear masks, it can be 6 times higher. So definitely, we should wear masks. But after having seen Boeing and Airbus presentations, it's really, I believe, it's really reassuring that we have used similar but different assumptions, different methodologies, different cabin sizes and seat arrangements, and we have basically arrived to similar conclusions that the ambient inside or the environment inside an airplane is very safe. So I believe this gives robustness to all our analysis and credibility to it. So if you need, I dare to say that if you need to travel, if you want to travel and you want to minimize the chances of being infected by COVID-19, put on a mask and get on an airplane. Thank you.
Great, thank you very much for that. I think we've lost David again, so I'll take you just through a short transition period. If we can have the next slide. Oh, you're back, David.
I am indeed. Sorry for that, but
like magic.
There's little to say here except to echo what's been said, and that the risk of onboard transmission appears to be low, and to some extent this represents the features of the aircraft that were designed in. And certainly it's enhanced by mask wearing. So in addition, there are many precautions along the travel experience that we've introduced that will help people to travel safely in this COVID period. So thanks, Tony, back to you.
Thanks, David. Yeah, and just to, I suppose, reinforce that this briefing is about one element of all of the protections that are being put in place to make travel safe. So I won't go through all of those, but just as a reminder. And then lastly, and I think you probably get that from the parties that we have on this call. If we can see the next slide, there are lots of people that are looking into the various issues around trying to make travel safe. These are just some of the organizations that IATA, Boeing, Airbus, and Embraer have been collaborating with throughout this crisis to try and ensure that travel is safe. So before we go any further, I see there's some more questions in the queue. We'll get to those in one minute. But literally, we have a sort of a wrap-up video that we'd like to show. So Calliope, if you can put the video on. Just recalling some of the key messages from today. Great. So we'll now start into the questions. So we have a first question, which is asking the manufacturers, as a result of this study or these studies, have you changed any of your recommendations to airlines or your approach to aspects such as filtration and design? And it's open to Boeing, Airbus, or Embraer. Maybe Luis, since I can see you on top, do you want to try to take that first question?
Yes, thank you, Tony. We basically are working with airlines, collaborating on passengers' movements in the airports and planning and deplaning. But we did not change any recommendation in terms of maintenance intervals or things like that. We're also collaborating on them in other, let's say, means of contamination like contacts and clean labs and sterile labs, but no recommendation in terms of maintenance or the machine itself.
Do either Boeing or Airbus have something different to add to that?
Well, I think I'll add a couple of words. First is we're working through the ICC-AIA ad hoc working group to make sure that we're providing consistent recommendations to our operators. So we have prepared some documents and shared with our operators things like increasing the airflow in the aircraft to its optimal settings in order to achieve the effects that we're seeing here in the analysis. It's not really a physical change to the filters or anything else. It's more about the settings of the airflow in the airplane to ensure that they're operating at the maximum settings to make sure that there's maximum airflow. The same thing, the same conditions during taxi, takeoff, landing, and at the gate, so that you can maximize the dispersion of the particles. It's also important to understand that these analyses are not all done at like the premium settings or the absolute maximum settings. We do not only provide a variety of settings as part of the analysis, but we also take a significant knockdown in I'll say the effectiveness to ensure that our results are very conservative. So it's important to know that we're trying to account for as much real world situation as possible.
Okay, thank you. We have a question about social distancing. And the questioner says that in many places we see bars being closed again, restaurants required to practice greater social distancing, etc. How did today's presentations apply to social distancing on board the aircraft? And I suppose the obvious question would be leaving open the middle seat. Maybe Bruno, we haven't heard from you. Do you want to take that question?
Yes, of course. I think that's what we try to demonstrate today, is that the social distance on board an aircraft cannot be measured by taking a 6-foot meter and measurement. The social distance on board an aircraft is ensured by the airflow, which is washing away particles and droplets. And clearly, that's the best protection that you can get on board an aircraft. So the recommendations that are given today in bars and restaurants are generally in places where the ventilation is not cannot be compared to the degree that you can find into an aircraft. And that's really what makes a big difference between an aircraft environment and a classical, I would say, ground environment that you would find into a building.
Okay. Are there anyone else want to comment on that?
Yeah, it's important to understand that it's a system. So the airplane has the airflow, it has the filters, it has the architecture where the air flows from top to bottom. All of these things work together to provide protection to the passengers. In a bar or a restaurant, there is airflow and filters, but they're usually to a different standard. Building standard is much different than an aircraft standard. And so the 6-foot distancing is really developed based on the environment that people are in their everyday lives, in buildings or in houses or in outside of the park, it just doesn't apply in the same way to an aircraft, and that's why we've done these detailed analyses in order to show that the design factors in the airplane really do make a significant improvement in the protection of passengers with regard to aerosol transmission.
Okay. Thank you. We have a very practical question asking about how the tests, the real life tests are conducted. And maybe I'll throw this to Luis Carlos. How do you ensure the safety of the coffers and breathers when you're doing these tests on board? Do you test them for COVID, for example, before the tests are conducted?
In our case, we did not do the tests with people. I believe my colleagues here have done that. We have done simulated tests with the mannequin coughing, let's say, simulating a cough, given, medical papers and models that are available in the industry and even recommended by the organisms in our industry. And we have measured with devices, not really around a person. So maybe my colleagues can comment that, but in our testing, we did not expose the real people.
Well, in our case, for sure, thanks for the question. Of course, the safety of our employees in Airbus is of utmost importance. So we took the precautions, and we had the health and safety doctors, occupational doctors with us whenever we conducted such a test. And yes, the people were tested to make sure that they were not infectious or that were not creating risks. And by the way, we did not play, I would say, with the virus, of course, either. But we used smoke to represent, I would say, the airflow that you could experience in the cabin. to make sure it was there was no consequences, I would say, for the were in the test range.
Yeah,
Okay,
we've done a variety of tests, both, and of course, as Bruno mentioned, we're not going to put passengers on an airplane with the coronavirus, right? So for the airplane level testing, we used a simulated chemical that has a similar particle size as a virus. We've also done smoke testing as well, but in addition, we've actually done surface testing using MS2, which is a live virus that is human safe. And so I want to basically let people know that we've done a whole variety of things. We've done analysis, we've done testing with simulated virus-sized particles, we've done some testing with human-safe live viruses in order to make sure that we completely understand the environment. And it's important to understand that the work that we've been all talking about today is the management of aerosol-sized particles in the cabin. The larger droplets, as Bruno mentioned, fall out of kind of the air because they're heavier and they drop out right away. The aerosols are the ones that tend to remain in the air and transmit through the cabin. And these are the ones that we're measuring from the coffer to the breather. And these are the ones that are evacuated very quickly through the system as we have complete the volume of air exchange in the cabin every 2 to 3 minutes on board these aircraft.
Thank you. We have a couple questions about masks. So, Luis Carlos, you had some figures in there about the difference between a mask wearer and a non-mask wearer. And the question is for Boeing and Airbus, did you find a similar range of difference that Embraer found in their research?
I could honestly, I cannot remember the exact figure that we found with or without mask, but for sure, we still recommend to wear masks on board the aircraft. The answer is a bit more complex than just saying with or without mask, because there are cross effects also, and you want to know whether the people are wearing it correctly, not correctly, and there are some complex, I would say, air principles. So in a nutshell, yes, the mask is required, but I don't have the exact figure on top of my mind on this one.
And did you want to comment?
So we simulated the masks that we knew that there's a variety of masks, right? So we didn't use like N95 masks or something that were really considered high end. We took a significant knockdown on the effect of the mask during our analysis to ensure that we accounted for a large variety of mask types. You could say perhaps that it was similar to one of those blue surgical masks that still has air leakage around the outside in order to make sure that we've accounted for what we consider to be an average real life situation.
Okay. We had a question asking about the barrier that the seat provides, and we had another question about the gasper, and maybe do you want to talk to how those two features of the cabin impact this research? Bruno, maybe you want to take that?
Yeah. So on the gasper, when you read the recommendation that we have made, our recommendation was not to use the gasper, to turn them off. And what I'm going to tell you is also specific on the aircraft, because the architecture, as Dan said, and as Mr. said, is quite different from one aircraft to another. So we cannot have one answer that fits all needs. On the Airbus cabin, our recommendation was to turn the gasper off or to minimize their usage, because in fact there is an optimum position of the gasper that is going to help remove the particle, and it's full open, going onto your knees. And there is an adverse position, which is the gasper blowing to your face, full open as well. And it's very difficult for a cabin crew in operations to control that each of the gaspers are going to be put in the right position, the right angle, right orientation. So as a conclusion, from an operational standpoint, we said it's better to close them. That's the average position, that it's easy to control for the crew, and that is going to minimize, I would say, the exposure and the risk for the people. Wow.
Yeah, I think through our studies, we found that the use of gaspers is very architecture dependent. So the results that Airbus is going to have, the results that Embraer is going to have, are going to probably be different than the results that Boeing has, because we have different cabin architectures, different airflow. And so the results that we found is there's very little difference between gaspers on and gaspers off, and it is different between a single aisle airplane and a wide body airplane. And so we're not making a specific recommendation on or off, because we think that they were designed for passenger comfort, and we think that they're still appropriate for use for passenger comfort, because it doesn't make a large difference one way or the other if they're on or off. And as Bruno mentioned, it's very hard to control that with all of the passengers on an airplane. So in the end, we believe it makes little difference.
Okay, thank you.
Yeah, if I may complement, in our studies, we also concluded that the gasper, let's say, influence is not big. So we are not making any recommendation regarding gaspers either.
Okay, thank you. We have a question. I think it's a really important thing to be precise on. The questioner says, is the HEPA filter effective in filtering out virus particles? And do you have any estimate of how much of those particles are caught? Just to make sure that we're really clear on that, maybe, I don't know, Dan, do you want to start us off on that?
Sure. So in working with our filter manufacturers and understanding the levels of MERV rating, it's MERV is the ratings for filter effectiveness. We understand that the filters that are used on the airplane, which are MERV 17 plus, are effective at filtering out virus-sized particles. So if you look at the size of a particle, I think that Luis had a particle size on one of his charts. The filters are designed to filter out that size of particle when you're talking about MERV 17 and plus.
Okay, thank you. I think another really important precision, and I see we've had a few comments even after we've addressed it in this briefing. So just to be clear, when we talk about droplets, we're also talking about small droplets being aerosols. Is that correct?
Right. Yes. The standards, I would say, or the standard definition for aerosol is that it's particulates or droplets which are going to be smaller than 5 microns. And you can see that we are considering, in our case, and I believe it's the same from my colleagues, from what I've read, in our case, we're considering size of particulates which are from 1 to 750 microns. So the aerosol band, which is covered by our model, is 1 to 5 microns. So it's fully covered, yes, in our model.
Okay, thank you. We have a question about the air exchange and the rate of that. So I know the industry has often talked about how frequent the air is exchanged. Maybe if we could go into a bit of depth as to what the frequency is and what that means for the air that people are breathing on board. Maybe Dan or Luis, you want to take that?
Sure.
Yeah. Please go ahead.
Why don't you start?
Okay. So as I have presented in one of the slides, every 2-3 minutes we inject in the cabin the same volume of air that fits in the cabin. But of course, we cannot say that we have fully replaced that air, because there is a recirculation, which is about 50%. So 50% of the air that comes out of the cabin, goes through the filters, the HEPA filters, and is returned to the cabin. And there are reasons for that, even comfort reasons in terms of humidity and things like that. The outside air is very dry. But in any case, every 2-3 minutes, we insufflate in the cabin the volume of the cabin, which is much higher than in any other environment. So these are basically the data we have in our airplanes.
Yeah, I mean, the same physics occurs in the Boeing aircraft, and I'll say for Bruno, the Airbus aircraft. It's the volume of air exchange is really important, and because that disperses the particles in the air, and it also brings the particles out through the vents or into the HEPA filters. We've measured on a 737 that a cough event. We've eliminated all of the measurable cough particles after about 90 seconds after a cough. All of them are out of the air system into the outflow. This high volume air exchange that we're talking about, whereas we're not saying every single molecule of air is gone from the cabin after 2 or 3 minutes. We are saying that there's a large volume of air movement that disperses the particles, and we don't see measurable particles in the cabin after about 90 seconds on a single aisle airplane.
Okay, thank you. We have a question about, I guess, relative risk. So the questioner says they understand that the airflow helps to reduce the number of droplets, but even if one reaches a passenger, can they not still be infected? And does that not undermine what we're trying to say here? Maybe, David, did you want to take that to start?
I was writing a response to another question. Can you give it to me again?
So the question is basically on relative risk. So it's saying that it's impressive to see how much airflow reduces the number of droplets in the aircraft, but even if one reaches a passenger, they could be infected. So doesn't that undermine the whole presentation?
Life is a question of dose, isn't it? And there are some viruses like measles, which are exceptionally contagious, and just a few virus particles are known to be able to lead to somebody becoming infected. I haven't seen anything to suggest that anyone thinks that's the case to the same degree with COVID, but it is, in all of these things, it's a matter of chance. When you're up close to somebody who's unwell and coughing in your face, you're going to be getting millions, billions of particles. And we are talking in this discussion about a scenario where you're down to maybe just single or double figures of particles. So, you know, it's about dose and risk. So nobody can say absolutely. The speaker said this, exactly how many particles is the minimum to create an infection. We don't know. But we're certainly managing the risk to a huge extent. I hope that's clear.
And I suppose the overall point would be that with all of the controls that are in place, the cabin environment is as safe, if not safer, than most other indoor environments.
Exactly.
Which is back to the relative risk, and that's the way we wanted to approach this. Yep.
Yeah, I think it's important to be clear that we're not saying that there's no risk. That there's risk in everything that we do, and all of our presentations are really focused around making sure it's clear what the relative risk of aircraft travel is compared to other activities that we do, and people can make a choice about whether it's important for them to take on that risk. But the risk that, and we all are reinforcing this, the risk of air travel, contracting COVID during air travel is really, really low. And it's important for people to understand that compared to other things that they do every day.
Great, thank you. We have a couple of questions on environmental features within the cabin. So how does humidity or temperature impact the findings of these studies? Maybe Bruno, you want to take that to start?
I would say that the first positive thing is that if there is more evaporation on board the cabin, so the evaporation is going to be extremely positive to wash away the virus from the cabin. So I would say a dry air, relatively high temperature, helping that evaporation will help, and that's typically what you can find in aircraft as an environment. So it's probably also a reason why it's a safer place to be. Then, of course, the pressure, the pressure at which the cabin is operating. You know that when you're flying, you're not operating at ground pressure. You're operating at a pressure which is representative of roughly 2,500 meters. And there as well, the lower pressure in a cabin is going to fight the buoyancy of the droplets in the air. So the trend of the droplets will be to fall down more easily in that case, which is also very important. And as we are having this top to bottom airflow as well, we are maintaining the heat on your feet. And by maintaining the heat on your feet, we are also fighting against the natural buoyancy of particles over the body, which is the source of heat wherever you are. So all this is going to help keeping the droplets out of your breathing zone, basically. So all this is important, and by the way, all this is quite positive when you look at an aircraft cabin compared to a normal environment.
Yeah, the simulations that we did accounted for the low humidity in the cabin, the temperature in the cabin, all of these things were accounted for. So when we talk about the results and the relative risk comparison, we've accounted for the aircraft environment as part of that.
Okay, thank you. We have a question on HEPA filters. Maybe Luis Carlos, you want to take this? The question is, how often should the filters be changed, and have the recommendations changed as a result of the pandemic?
Yes, thank you, Tony. Well, the recommendations have not changed because they were good enough. So the intervals that we have been using for years, they assure this very, very high efficiency level, 99.9 plus percent. So no changes. In terms of the frequency of changes, this varies from installation to installation. It also varies from the environment you operate, if you have sand, if you have humidity, and so forth. But you can say, you can take an average of like 3,000 hours of flight for the replacement of the filters, which is a little more than a year maybe for a commercial airplane.
If I may, just to complement on one point, you have to understand how the HEPA filter works. So as you have this barrier, and as the dust and the particles are going to arrive in the barrier is going to be clogged. So in fact, strangely enough, the more you spend time operating the HEPA filter, the more efficient it's going to become, as it's going to continue to filter more and more. The limit to this is that at one point, even the air will not go through, so you cannot ensure the correct airflow on board the aircraft. So that's why we changed the HEPA filter. But keep in mind that the HEPA filter, the more you accumulate particles into it, the more efficient it's going to be as a filter.
And then when a HEPA filter is changed, there is a procedure with personal protective equipment, et cetera, in order to change the filter to ensure that it's the mechanic is protected during the process as well. So I agree with my other colleagues that filters get more efficient, HEPA filters get more efficient over time until they reach a point where there's not sufficient airflow, and then they're changed, and that frequency of change has not been adjusted during the pandemic.
Okay, great, thank you. I think we have a question for David. So the questioner asks how we came up with the 44 confirmed cases. And they have a specific reference to an Emirates flight to Perth with something like 19 potential reported transmissions. David, do you want to handle that?
Yes, sure. I've actually typed a response there. There have been a large number of reports, media reports through the year of apparent numbers of people getting off a flight when infected, but that's very different from a suspected transmission during the journey. So in fact, the table I showed you referred to 6 flights into Hong Kong where there were 85 people who tested positive after the flight. But when they followed them up, those 6 flights, there was only one who was thought to have been an in-flight transmission. So this, I believe, was the case with EK420. The Western Australian health authorities are all over this because they were actually the authors of the Speak et al. Paper, the one about with the cruise passengers that had up to 11 secondary cases. So they're certainly on top of all of those potential cases this year. Just to correct myself, the Dubai, Hong Kong ones, there were 2 possible in-flight transmissions out of 85. Yeah. Thank you.
Okay, great, thank you, David. We have a couple of questions just asking if the slides are available. We've sent out a press release. The slides will be on the IATA website, as well as the full recording of today's presentation. So all of those materials will be available for you. We had a questioner asking about potential design changes needed to the aircraft. For example, are any of the manufacturers thinking there's a need to try and put air curtains into the aircraft to change the way that the airflows are to further isolate droplets? Maybe Bruno, I see you nodding. You want to get that?
We made a huge amount of study cases of whether this could be done or not. I think the airflow in the aircraft has several functions, and one of them is to isolate passengers one to each other. But if you go too much into isolation, then you're creating problems of thermal comfort. It's always a balance that we're trying to have. And today we consider the airflow is safe enough, I would say, when you look at the data that we have. As I said, we are still considering the case of the gaspers. Maybe we can do something a little different, but there again we have to be careful because we could imbalance the thermal comfort. And really, when you're not in good thermal comfort, staying in aircraft even for an hour, freezing to death because you're sitting and not at the right place is extremely uncomfortable. And we tune, in fact, the temperature seat per seat with our design of airflow. So it's really very, very fine work. We have to look whether we want to create an imbalance into that or not.
Hello, Luis Carlos or Dan?
I would just say it's exactly the same for Boeing. Totally agree.
Great.
Yeah, for us the same. So no curtains don't seem to be, let's say, the best alternative. We are looking at investigating other things like tissues that would kill the virus on the armrests and lavs, but we're still, let's say, analyzing those.
Okay, great, thank you. We had a question, an interesting question, saying, what can other modes of transport learn from all of this research that we've done on the cabin environment? Is there anything for trains or buses that they could take into consideration?
Well, we have to be humble on this one. Now it's difficult to lecture others on what they should do or what they should not do. I think honestly, the main difference I see is not necessarily on the features. Well, there are, of course, big difference in the features. But one thing that we are lucky with, and I'm really in touch, is that we have a crew on board the aircraft. And I really want to thank them because they are essential to maintaining the control over the passengers, I would say, to make sure that people behave in a normal manner. And they're also essential to enforce the regulation and the rules on board the aircraft. So I think they are also very important protective measures for us because they are limiting the movement of the people. They are also asking to, and they are enforcing the mask wearing. And these guys, these men and ladies are doing a great job to help also the safety of all on board the aircraft.
Yeah, absolutely. I want to reinforce what Bruno said. For passengers, we're talking about a couple of hours maybe on a flight. for the crew, it's a workplace environment, and we're working very closely with the operators, the crews, the unions, in order to make sure that we're keeping as absolutely as safe a workplace environment as we can, because they're in this every single day. And we've had a lot of discussions with these groups, and we've actually found that the transmission rates amongst the people that are in the airplane every day or in the travel environment every day is actually lower than the destination cities or the departure cities in general. So it's another kind of layer of evidence that the travel system is actually safer than, as a relative risk perspective, than other places that you might go.
Okay, great, thank you. We have a question about when an aircraft is de-iced. Is it not true that the airflow systems are shut off during that time, and does that pose any difficulties for the analysis presented today?
Well, when you look at the recommendation today on the air system, at least on the Airbus side, because once again the systems are slightly different, but we are recommending to keep the air system at norm, not to put it at high, not to put it at low, but to keep it at norm, and it can withstand some period of non-operating for I would say a reasonable time. Okay, and for sure, we would rather have the air system always running on, but it can also withstand that we don't run it for a few minutes. That's okay. The main part, in fact, the main recommendation that we are all giving, I believe, is that it should be started before people enter the aircraft, so that the flow is established, and that's also a very important predictive measure. Our magnitude is 10 minutes before the passenger board the aircraft, and it should be turned off when the last human being has left the aircraft. So the one who leaves the aircraft turns off the air conditioning and the airflow. These are really what is going to make a big difference compared to other cases that we see.
Okay. We have another question talking about when passengers eat, they need to obviously remove their masks. How does that impact the analysis presented today?
So we've done analysis with masks on and masks off in many different configurations. We're again, I'm sounding a bit like a broken record, but we're talking about relative risk, right? So having a mask on is going to reduce relative risk. Having a mask off, I think my Embraer colleague mentioned it was about 6 times different. I've seen some different factors about relative risk. We believe that the particles that enter the breathing spaces is extremely low based on the air system, the things we've talked about today. Masks are one more step to reduce that, but if somebody's taking off a mask to eat, it doesn't mean that it's become an unacceptable risk. I mean, it's just a small relative risk. So I don't see a problem with eating on an airplane, certainly. And I think it's all about at this point it's all about personal kind of personal commitment and how each participant, each passenger participates in the system. And when wearing masks, it helps protect others and it helps protect yourself, and it should be done when practical. And I think it's a common sense approach.
Great, thank you. We have a couple of questions, maybe for David, talking about or asking about the airport environment, and is the airport potentially more challenging in COVID than the actual aircraft? David, did you have anything you wanted to say on that?
Well, it's important to consider the whole journey, as I think I said in the introduction. On the one hand, there are more challenges in the airport because we don't have the same control over the air supply, and people are constantly in motion, and they may have more face-to-face interactions. On the other hand, they have the capacity to achieve distancing to a greater degree, and that's certainly being encouraged with all of the measures that are being introduced at airports. and every step of the journey has been looked at by our colleagues at Airports Council International and by the individual airport operators. So I don't think it's more or less. It's as well. All of those things have to be considered. Somebody else asked about what about the other end of the journey, and one of the things that we're aware of is that when people arrive at their destination, they're just a little bit less likely to be slow and cooperative in terms of how they achieve their distancing. So that's another piece that has to be managed carefully.
Okay, thanks, David. We had a couple of questions asking about surface transmission and what type of activities, for example, UV lighting, etc., the manufacturers might be exploring on that. Maybe Dan, did you want to say something to that?
Sure. There's an extensive amount of work going on to help minimize minimize surface transmission. Clearly, the first step is chemical disinfectants, and I know all of my colleagues at the airframe manufacturers are working to ensure that the chemicals being used are both effective against the virus as well as safe for the airplane. But we're also looking at ultraviolet light. We're looking at thermal disinfection or using heat to disinfect. We're looking at ionization or electrical charge in order to aid in disinfection, and also longer lasting antimicrobial surfaces or antiviral surfaces where it could have a spray that might last weeks or months that attack the virus when a virus comes in contact. So it's a little bit like designing a toolbox that our operators can then take out the tools that are going to be most effective for their operation and fit within their operational parameters to be an effective way at combating surface transmission.
Okay.
Yeah. And if I may complement on one point, we're also dealing with humans there, and we know that psychology is also very important. So in the disinfection process, there is not only what the airline can do for you, but there is also what you can do yourself to protect the others. And here we're also insisting on wearing the mask, but in many cases, sometimes it's better just to give a wipe to somebody and to ask this person to complement and to continue to disinfect the seat this person is sitting in, knowing that it has been already disinfected, but from a control, give control to the passengers. You can give a wipe to the person and ask this person to do the cleaning, also the complementary cleaning that she or he wants to do and he thinks is important. So the psychological and the sense of control that we give is also something that we need to work on to build the trust that people have that the place they're sitting is also clean.
Thanks very much. We have a question about in-flight service. Considering the wearing of masks as a prerequisite and the results of the research that we've presented today, what are the implications for a return to normal service inside the aircraft, normal circulation of passengers inside the aircraft, or use of the washrooms?
Dan, you want to?
Well,
whatever.
That's going to be tough. I wish I had my crystal ball that I could tell when things were going to be back to normal, but I can't. I think from my perspective, it's about continuing to monitor relative risk. It'll depend upon risk of, I'll say, the prevalence of the virus in the departure city and the destination city. It could depend upon whether there's a vaccine available. Certainly, it could depend upon a lot of different things. I think in the near time period, we're going to continue to see masks and other preventative measures being put in place in order to make sure that not only does is it safe from virus transmission, but it also feels safe from virus transmission. We're talking about building confidence in the traveling public, and I think Bruno alluded to making sure that people have a sense of control and they have a sense of feeling that it's disinfected, and that's really important, as well as the underlying foundation that it absolutely is a low risk place to be. So I think I'm not going to predict how long it's going to be like this, but I think until we have some bigger issues like a vaccine and things, we'll probably see some similar preventive measures remaining in place.
We have a question asking about some of the seat dividers that have been promoted. So the idea of putting some plexiglass between seats in the cabin. How does that, would that interfere with the airflow? Would it help? Any of the manufacturers want to comment on that?
I can take that one if you want. So we've studied that one as well, the seat dividers, and we do not recommend to use them for several reasons. Either they are very small, and then of course they are not going to protect from you of anything, or they are large, and if they are large, that means that they are going to distract the flow and disrupt the flow. And by the way, they are also posing extra challenges, which are they need to be cleaned. So it's an extra cleaning work that it needs to be done there and properly cleaned. And also, well, we are in aircraft, so there are still some emergency evacuation procedures that we have to respect. And when you look at these kind of devices, they also pose some other safety problems in terms of evacuation. They could also pose some safety problems in terms of fire propagation into the aircraft in case of fire. So all in all, the benefit that they would bring is zero, to be clear. And we see a lot of extra challenges that they are posing. So we are not investigating any more these kind of devices, and we are not recommending them to be installed on the aircraft.
To reinforce what Bruno said, oh, go ahead.
No, go ahead. Go ahead, Dan, please. I can talk later.
I want to reinforce any change that's made to the aircraft has to account for not only the problem that you're trying to solve, like transmission of a virus, but also all of the other impacts to aircraft safety and operations that, and there's many design considerations. Bruno mentioned evacuation, flammability, reach to an oxygen mask. There's a lot of things that have to be considered when adding something maybe as simple as a shield between seats. And so we haven't seen the benefit of doing that based on all of these other factors at this point, although we continue studying and trying to improve our aircraft as we go forward.
Yeah, I was just going to agree and concur with Bruno and now with Dan that it's like the curtain. So you know, it really brings more negatives than positives, including for the virus propagation. It's another you know, another transmission element with all you know, the downsides of disrupting the flow that has been so beautifully optimized to provide for a clean cabin. So we don't think, like the curtains, we don't think these are good ideas.
Great. Thank you all very much. We've just passed 6 o'clock here in Geneva. We're sort of an hour and a half into the briefing. That was the time we planned. I see there are still a few questions in the queue. If you have a look at the release, we have contacts for the communications departments in each of Boeing, Embraer, and Airbus, plus IATA. So feel free to reach out if you have any further questions. As I said earlier, all the documentation for this will be available on the IATA website. And we thank Boeing, Airbus, Embraer, and Dr. Powell for joining us for this briefing. We encourage you to have a look at the materials and fly safely. Thank you, everybody.
Thank you all.